Okay, so hi, welcome to this next video in linear programming. So previously we have been discussing some geometric features of polyhedra, and in particular we showed that polyhedra are convex. Where we're going with all these geometric features is that we are trying to show what the simplex algorithm is doing from a geometric perspective. And so that's our overall goal with this geometry thing. And in order to achieve that goal, we need to talk about something called extreme points of polyhedra. That's the next important geometric feature we need to show. That's the main one, really. So to even talk about extreme points, though, I first need to introduce you to this idea of tight constraints. And so that's what this video will be on. It's an introduction to that idea. So let's get started with this idea of tight constraints, and let's see what that is. Just here's the definition. If you give me a system ax less than or equal to b and a feasible point x bar, so ax less than or equal to b is presumably that will be the system of inequalities associated to the linear program that we have, and the feasible point x bar is the feasible point in our linear program, so it satisfies all these constraints. So if we have such a system and such a feasible point, then we're going to say a particular constraint, so this is a system of constraints, then a particular constraint is tight for this point x bar if when I plug in x equals x bar here, this particular point, into this particular constraint, not only does it satisfy the less than or equal to constraint, but it actually satisfies it with equality. So to even talk about what a tight constraint is, I need to be talking about it in terms of a particular point x bar. So you give me the feasible point x bar, and then I will look for all the constraints that when I plug in x bar, the constraint holds with equality. And those constraints are called tight constraints for that point x bar. Okay, so geometrically, the idea is that if we have a single less than or equal to constraint like this, that's a there's a hyperplane that splits space into two halves, and there's the good side of the half space. Sorry, there's a good half space and a bad half space. The good one that's the one that satisfies the less than or equal to inequality, and then if we satisfy it with exact equality, that means that that particular point that satisfies it with exact equality lies on that boundary, or it lies on that hyperplane. Okay, so a point so a tight constraint for a particular point means that that point lies on the hyperplane associated to that constraint. So that's geometrically what's happening. And if you can see that if we went any further in that direction, we'd cross over to the bad side and we'd violate the inequality. And if we were any further to the left, we'd have a strict inequality. But we're lying exactly on the boundary. Okay, so let's just take a look at a few examples of this. So here's the example of the linear program that we've been working a lot with, although I still haven't filled in an objective function because it's still just not really relevant for us right now. What's relevant is the system of inequalities. So I've highlighted a point here, x bar being 0, 2, and so that's this yellow point right here. And so we can take a look at what are the tight constraints for that point. And so I've highlighted those in green here. These are the tight constraints. And so you can see that this yellow point, it lies in the feasible region, but it lies on two hyperplanes specifically. This leftmost vertical line and this upper horizontal line. And it lies on both of them. And so for that reason, because it lies on both of those hyperplanes, that means that both of the corresponding constraints here should be tight. And so, if instead I picked the point 0, 1 instead, which would have been right here, then it would have not lied on that upper hyperplane up there, and it would have just lied on this left one, so there would have only been one tight constraint. But instead we picked this, it's at a corner there, there's two hyperplanes that we're lying on, and so there's two tight constraints. And you can see algebraically as well, when you plug 0, 2 in to these constraints, it holds with exact equality. 0 times 0 plus 1 times 2 is 2, which is exactly equal to the right-hand side. And similarly, minus 1 times 0 plus 0 times 2 is 0, and that's exactly equal to right-hand side. And then, for example, 1 times 0 plus 2 times 1 is 2, which is strictly less than 3. So it still satisfies all these constraints, but the rest it satisfies with strict inequality, and for these two it satisfies exact equality, and that's corresponding to the fact that it lies exactly on those two boundaries, whereas it does not lie on the boundary of any of the other hyperplanes, which correspond to these other constraints. So that's really all that's going on there. That's the entire idea. So in general, you give me the system ax less than or equal to b, and you give me a point x bar, and I'll just highlight the tight constraints. So I have to know x bar, and then I look at the ones that hold with exact equality, and it's those particular constraints that get highlighted in green. They're tight. Here's some notation. Some notation is A equality and B equality. So A equality, superscript equality here, you can see. This is a submatrix of the matrix A. So I have the system here, and I have the point x bar, and then I've highlighted the tight constraints. A equality is going to be the submatrix that's consisting of just those tight constraints for that point. Okay, so I just take those highlighted rows and I just smush them together, and that gives me this matrix A equality. And similarly, B equality, it's just the components on the right-hand side that got highlighted for the tight constraint, and I just smush those together, and that gives me this subvector B equality. So this is a submatrix and a subvector, respectively, corresponding to just the tight constraints. And you can see then that it has to be true that A equality times x bar equals B equality, and that's just because this is just a subsystem of the overall system of inequalities, and this is corresponding to the ones that are tight for x bar, so the ones that are satisfied with equality, and so that's why we have this equals to for this overall system when we plug in the point x bar, because remember, we generated these tight constraints based off of this point x bar. So it's A equality times this particular point x bar is equal to B equality. Okay, and so just with that notation, let's just try one other example. Here's a genuinely different example from the one that we've been referring to over and over. It's just different constraints here. They're all less than or equal to. I still haven't filled in an objective function. It's just a placeholder here. We don't need it right now. But the thing that we are concerned with is these constraints, and if you plot that all out, this picture is basically what you would get. And I'm picking the point x bar to be 3, 0. So that's this yellow point right here. And you can see that it lies on only one boundary, which is this bottom boundary, which is corresponding to a boundary x2 being greater than or equal to 0, or in other words, x2 being negative x2 being less than or equal to 0, because we write everything as less than or equal to constraints. So that's this bottom constraint right here. So this fifth constraint here, there's 1, 2, 3, 4, 5. This fifth constraint is the one that's tight for this point x bar here in yellow. So what should the matrix A equality be? Well, it's just the submatrix of tight constraints, and there's only one. There could have been multiple constraints that were tight, but in this case it was just one, and it was this bottom constraint, 0, minus 1. So A equality, the submatrix, is just a one-row matrix, and it's 0, minus 1, this right here. And B equality is the corresponding component on the right-hand side, which is 0. So it's just a one-component vector. And then you can see that A equality times x bar is B equality. That has to be true in general, and you can just verify it. This example, it's just one constraint to check actually. So 0 times 3 plus negative 1 times 0, that's 0, and the right hand side is 0, and that's consistent with the fact that this point lies exactly on this boundary. Okay, so that's how it works, and this is the notation that we use for talking about the submatrix of tight constraints. So we'll be using that notation in the future. So here's an important thing to point out. Just note that the rank of that submatrix, A equality, the submatrix of tight constraints, that has to be less than or equal to n, where n, as usual, A is a matrix, and it's so the whole matrix is A, and there's m rows, n columns, as usual. That's just the notation for rows and columns, and so A equality, being a submatrix of of the overall matrix, it has n columns as well. So the rank has to be less than or equal to n. That's just automatic because we only have n columns for this matrix A equality. So the important observation is, so we can never be more than n in terms of the rank. The rank of that matrix is going to be more than n. But when that rank of that matrix is exactly n, then we can conclude that this system, A equality times x equals B equality, it has a solution, but that solution is unique. It has the unique solution x equals x bar, where x bar is that specific point that generated the tight constraints. So you pick the point first, and then you get the tight constraints corresponding to that point, and then you're looking at that matrix which corresponded to that point, and then this system that you get, it's just the subsystem of the overall system, and yeah, because this has rank n, that's saying that all the columns of A equality are linearly independent, and so since that's true, then there can only be at most one solution, but we know that there is we know that there is a solution. It's x bar. That's by definition of what A equality and B equality are. They are the system of tight constraints for that, so x bar has to satisfy this, and since the columns are linearly independent, there can only be at most one thing, so there's exactly one thing, which is this point x bar. So that's what happens when the rank achieves that upper bound of n. So yeah, so we'll use this fact. The rank of this submatrix is pretty important in terms of talking about future geometric features that we'll need. But those will be for future videos. So that's it for this video. So thanks for watching.